adapt it to some changes. Let's do all of that again, but in chapter 9, we just moved out of 8. We're going to do it for acids and bases. We've already done some discussion of acids and bases, but we've spent a lot of our time talking about insoluble salts. Okay? So, what we're going to go ahead and do today is several pages of the exam from a few years ago. Okay, when we used a different book and the subjects were in a different order. So this was a little bit earlier in the term, but we'll just run through the questions. All right, plus one that I'm adding right now. Question. Find the pH of 0.150 moles per liter HNO3. Okay, what do we know about HNO3?
It's a soluble salt. All soluble.
Well, all nitrates are soluble. It leads with an H, so it's an acid. And it's a strong acid. Which acid is it?
Nitric.
This is nitric acid. In the old-fashioned naming system, there is ick and there is us. And there's no numbers associated with that, other than we know that ick is more than us. So after we've done this, I'm going to ask you the same question again, but for nitrous acid. When we say that there's a difference in number between ick and us, what number are we talking about?
Number of oxygen.
Number of oxygens. In a polyatomic acid, putting oxygens around that central atom increases the acidity. Okay, so this is a strong acid, and because it's a strong acid, we are told, and it's true, we're going to have a little bit of problem with the book saying, yes, but you have to take account of this later on, but with what we know, the concentration of this nitric acid is 0.15 molar, but there's no nitric acid in solution. There's no HNO3 in solution. There's only H plus and NO3 minus, which means that my 0.15 moles per liter in my initial case it's gone, because it's all 100% dissociated. So go find me the pH. I actually don't know what the number is, but that looks reasonable.
Okay, I was like,
Yeah, just make this one up.
okay.
This is an add-on at the beginning of what we're about to do, because this is the last time we're going to see a strong acid for a while.
Oh, I like them. Fun and easy.
They are certainly easier. I mean, at this point, I don't think that we have to do anything more than that's H plus. Right. And the pH is negative log to base 10. Now, if the question says show your work, and you just write the answer, then you haven't shown me where the pH comes from, and you haven't shown me, you can say like 100% associated, or H plus equals this number. You have to show me some work. We're looking for corroboration of a number, so get your calculators out. Tell you when I'm not. What'd you get?
Okay, yeah. We got the same one. I'll just check. 0.0823. I don't think I'm.
We're allowed 3 significant figures. The only number in the entire thing. Now, if you go back all the way, I think it is to chapter 1, you know, about propagation of errors and significant figures. It says when you multiply or divide numbers, you get to keep this many significant figures, which is the smallest number of significant figures in the question. There's a rule for logs.
Yeah, oh, there is, I forgot about it. I don't know what it
So
is.
what? How many are you giving me?
We were getting
8.
824.
Okay. Let's have that be our answer. All right, we have a pH scale that runs from 0 to 7 when you're acidic, and from 7 to 14 when you're base. So we're here. That would be counted as a dilute acid, not concentrated. And it's putting a lot of H plus into solution. One of the things that we're going to take a look at today is that dilute acids actually do a better job of being acids than concentrated acids do.
Makes sense.
It does?
Well, like,
Well, tell me why.
because you have, like, it's easier to, like, spread out more if you have less of y'all. Like, since there's like 4 of us in the room, for example, it's easier for us to spread out than like 15 of us to spread out in a room.
I know what you're saying.
And it's
The
easier
more
for the
water you have, the more water there is to solvate the H plus, right? The acid wants to give its H plus away. Who's it going to give it to? It needs to be solvated, right? So if you have water, you can solvate the H plus. If you don't have water, you can't solvate it. So really concentrated acids will pump lots and lots of H plus into solution, but they do it with the hammer. They do it with their concentration. Dilute acids get to put their H plus into solution because there's water that will accept it. Okay, we have a number. Let's keep that in mind, that is fully dissociated, and we have a low pH, so our solution is strongly acidic. All right, I'm going to change one thing in the question. There it is.
Yep.
HNO2 is nitrous acid, us being less than ic, without a definable number associated with it. Sulfurous acid has 3 oxygens. Sulfuric acid has 4. Nitric acid has 3 oxygens. Nitrous has 2. So the us versus ic in acids just means 1 less oxygen. Nothing else changes. The number of hydrogens stay the same. There's no additional charges or anything. We're just going to drop an oxygen. And because I've lost an oxygen, I've weakened the strength of the acid. So now this behaves like a weak acid and is in equilibrium This is no longer nitrate. It's now nitrite. 8 means negatively charged and contains a specific amount of oxygen. That number is not mentioned. Sulfates have 4 oxygens. Sulfites have 3. Nitrates have 3 oxygens. Nitrites have 2. So, yeah. Ite means NO3 minus is nitrate, NO2 minus is nitrite. All you do is lose an oxygen, you don't change anything else, you keep the charge.
So X to 8 and us to 8.
Ik is to 8 as us is to 8.
I know, it's a fun time.
Okay, find the pH of this.
Do we have KSP?
No, there's no KSP because this is completely solid.
Okay.
We do need to know a value of Ka, the acid dissociation constant, and the acid dissociation constant is 5.62 times 10 to the negative 4.
Do we need to keep the X and do a quadratic?
You tell me. The initial concentration of this is 0.15 at 0 and 0, and I'm going to lose some of it, and whatever I lose will split evenly and make some of that and some of that. So at equilibrium, I have 0.15 minus x, and x, and x, and the value of Ka is H plus NO2 minus. Remember, it's products over reactants. Oh yeah.
We've done this one.
Okay. Which is x times x divided by 0.15 minus x. And now I have to ask, does this matter? Under what cases would it matter?
If Ka is really big or the concentration of your acid's little.
Okay. So the answer to the question, does it matter? We could either set that as a no or a yes. Let's do the yes. Yes, it would matter if Ka is what? And at 10 to the negative 4, that's kind of the region, that's kind of the world of weak acids. They're 10 to the negative 4, 10 to the negative 5. else do we have to worry?
When that concentration of your weak acid.
When this is small. So when the concentration of our generic, HA is just generic weak acid, we don't care. When it's very dilute, so when this number is small and that number is big, then it has an impact. Right now, I'm going to say, let it go.
Okay. Yes.
So that is x squared over 0.15, approximately, which is equal to the value of our Ka, 5.62 times 10 to the negative 4. Okay, so that number times that number is x squared. X squared is 0.15 times 5.62 times 10 to the negative 4. Which means that x is the root of that. And what does x represent?
The concentration of H plus.
The thing that we really want to know. The equilibrium concentration of H plus.
Dr. Gordon, why does it matter if your HA is very small? Is it because it makes the fraction larger?
Yeah, so we've got to think, if this Ka is 10 to the negative 4, then where's my equilibrium?
It's to the left.
Any number that is larger than 1, the equilibrium leans this way. Any number that's less than 1, the equilibrium leans that way. 10 to the negative 4, the equilibrium is here, it's pushing to the left-hand side. So not very much H plus going in. And so the question is, if I'm not putting much H plus into solution, then I'm not just detracting very much from here. So when my value is in the tenths and the hundredths column, the impact of my Ka might be in the thousandths. Okay. So basically, kind of look at it and say, if that's a couple of hundred times smaller than this, go ahead with the approximation. Now, our book, if not this book, the book in general chemistry was absurd. It said, do the quadratic, solve everything as a quadratic, and then solve it with the approximation. And if those two numbers are not significantly different, then go ahead and use the approximation.
Wow.
Which is completely backwards. It's telling you to do lots of work to prove to yourself that you didn't have to do lots of work. That's un-American.
Oh! There we go again.
That is hilarious.
It's just nonsensical. So the value of H plus is?
I got 0.0091.
Oh, H plus, sorry.
Yes.
Did you round it or you just left it 9.1?
Yeah, I went to 3.
How many significant? We're allowed 3, right?
Yeah, 3.
Okay.
0, 0, 9.
I actually think in my notes I only have this to 2, but because we've changed it to be 3. And is this an acceptable answer?
No.
No.
Well,
You need 0, 0, 9.
You need 2 zeros.
Oh, there you go.
yeah.
Is it an acceptable answer?
Well, it's not what the question is asking for, but what do you mean by acceptable?
It's a number, doesn't have a unit.
Oh.
I was like, what do you mean acceptable? Do you
the number for nitric acid?
0.8240.
No.
Oh, wait.
Not here,
Right
pointing to
there?
this bit. What was the value for nitric acid?
0.15.
Yeah, so 0.15 has changed. My first digit was here in the tens column of the decimal. And I don't have anything in the tens, and I don't have anything in the hundreds. I almost do. But my first digit is down here in the thousands. It's a lot less acid in solution now. A lot less. Gives me a pH. Okay. Something new. We did it in chemistry too. So there's the answer to this question. Go ahead and find the pH. Find the percentage ionization.
Oh, I know. What's the formula? What's the formula?
It's the simplest one.
I know, and I always forget, and I always get it mixed up.
It's how much acid, H plus is the real acid. How much acid do you have in relation to how much acid did you start with?
Okay.
So how many protons per acid? The percent ionization is H plus over HA. And because we're expressing it as a percentage, we're going to multiply it by 100 and give it a squiggly sign. Our book in this chapter uses an alternate expression, alpha, degree of dissociation instead of percent ionization. I'm sure they have a good reason. I'll have to have a read around that paragraph to decide why they are using degree of dissociation instead of percent ionization. This one is easier. Degree of dissociation has more terms in it. It tells us essentially the same thing. This is 0.00918 divided by 0.150, all multiplied by 100 squiggly sign.
We got 6.12%.
Which is kind of what we expect. Weak acids probably have single digit ionizations. Okay. The Ka is a constant. This number is not a constant. This number changes when that number changes. If I go ahead and make my solution more dilute, I should see that value go up. Should see the value go up. When I make this more concentrated, I should see that value go down. Now, when I make this more concentrated, that number goes up. And does that number go up or go down? Yeah. Stronger acid means lower pH. Bigger H plus. So stronger acid means bigger H plus, smaller pH. Okay. Let's move on. It's all going back on the board again in a minute, but let's just clear some space for it. I'm going to take the nitrous acid that I have and I'm going to dilute it. I'm going to take out 10 milliliters and dilute it up to a liter. I need to know the concentration of the new acid. How do I find that?
M1V1,
M1V1 equals M2V2. Let's have this be the undiluted and have that be the diluted. So 0.15 times, this is moles per liter, times 10 milliliters equals some number M2 times 1 liter. No. These are in different units. They're in different units. Can't use M1V1 equals M2V2 with different units. So I either need to turn liters into milliliters or milliliters into liters. How many milliliters are in a liter?
1,000.
There's my M, here's my milliliters, there's my milliliters. Milliliters cancel. And now I can trust my answer. But my new dilute solution is what?
0.0015.
Okay. Find its pH now. Yep. At equilibrium, some value X has been lost from the original concentration of the acid. And those X's are here. Ka, which is 5.62 times 10 to the negative 4, is equal to the H plus, A minus, over HA, which is X squared divided by 0.0015 minus X. Can we ignore the value of X here? No. No. That's 10 to the negative 4, and this is 10 to the negative 3. They are not far enough apart from each other to assume that the value of X is insignificant. So this is no longer insignificant. So we have to keep it in. Oh, you, so, while you're,
Oh, okay. Oh,
can you do quadratic on your phone calculator? Are you capable of doing that?
Mm-hmm. I'm an app for it.
Okay.
I think I
Okay. So while you're all clicking away, I will write the logic of how to do this on the board. Okay. So x squared over 0.0015 minus x equals 5.62 times 10 to the negative 4. That means that x squared is 5.62 times 10 to the negative 4 multiplied by 0.015 minus x.
I just put a small decimal. I don't know, I put like 0.003 or something like that.
Going to multiply into that bracket. This number multiplied by that number, it's going to be our first term, and then this number multiplied by that value is going to be our second term. So x squared is 8.62 times 10 to the negative 7 minus 5.62 times 10 to the negative 4x. Okay, so it just expanded that bracket out a little bit. And now I want to get everything onto one side so that something equals 0. So I'm going to move the equal sign here. I'm going to move these two terms across so that x squared, that minus 5.62 times 10 to the negative 4, when it comes across, changes sign from a negative on that side to a positive on this side. 5.62 times 10 to the negative 4. And this positive 8.62 times 10 to the negative 7 becomes a negative when it
You
moves
switched up
over.
the, you switched up these two.
Okay. Oh, I'm missing an X. There's my So we want this to follow a x squared plus b number of x's plus c equals 0. And if you have a calculator and you know how to do it, or an app and you know how to do it, then go ahead and do it. If you don't, then we're doing that by hand. That the value of x is equal to
6.79.
Oh, I'm not looking for a number.
Oh, you're talking about quadratic
Mm.
equation. Negative b
Plus or minus
square root of that.
4ac.
I don't.
No. B squared minus 4ac all over 2.
I don't know. I was going to look it up, so
I don't know why I'm doing this then.
All over 2a.
No, it's a stupid song.
I never learned that song. I'm so glad I did.
H plus, which is our value x here, is equal to the negative value of b.
Wait, no way, you're actually doing the quadratic
Yeah.
He's tormenting
Plus the square root of 5.62 times 10 to the negative 4 squared. plus 4 times 1 times 5.63 times 10 to the negative 4. All over. 2 times A.
What is one?
What's A?
1.
Okay. The numbers are in. What did you get?
We got 6.79 times 10 to the negative 4.
So, when I did it without the additional significant figure, my answer comes out as a 6.7. So that rounded down. You'll be rounding up to a 6.8. Let's keep it. All right. So our H plus equals 6.79 times 10 to the negative 4. That's 4 moles per liter. Okay. Comment on the magnitude of the H plus in solution.
It's a little.
Small. How much smaller is it than the nitric acid that was at 0.15? The acid at 0.15 was 0.15. 10 to the negative 4. This is 0.0000679. Yeah.
So is it 1,000 times like
Yeah. 6, 8, 9. Yeah, the same thing?
The quadratic, we got 6.79. But to what? 10 to the negative 4?
So would it be 1,000 times like
You double that and you get kind of a 14 out of it, which would put it here, times 10, times 100. Oh, no, yeah. 200 times.
200 times? Wait, can you run that back?
If I round that up to a 7 and double it, I make it be a 14. So 1, 4. I have a 1 here.
Oh, okay.
And then multiply my double by 10, and then by 100. So 200 times. It's about 200 times smaller. How does it compare to the previously dilute acid at that concentration?
It's about 10, a little like over 10. Because it was a previous, the other one was 0.00918.
Okay.
Like,
So we diluted it by 100 times, but the acid only changed by 10. Huh. We diluted the acid, the free acid, 100 times. But the amount of H plus that's in solution has changed about 10 times, maybe a bit, yeah, a bit more. Let's go figure that out. So, this number is now 0.00150, yes? Yeah, all right, so while that's still on the board, find pH. What was your pH?
I got 3.17.
Yeah.
answer before?
2.09 or 04.
Okay. So as the number gets bigger,
Mm-hmm.
the solution is less acidic.
Yep.
There's definitely less acid in solution.
Yes.
Okay. Let's look at its effectiveness.
Mm-hmm.
Percent ionization kind of tells us an effectiveness. This would be 6.79 times 10 to the negative 4 divided by 0.00150 multiplied by 100.
I got a pretty good size number for percent ionization.
Yeah.
45.27%.
Really?
Yeah.
Actually, I don't know whether I have it as part of my question yet. So this is, I'm taking what was on the test and I'm throwing a couple of additional things into every question. Wow.
Yeah.
that's
Yeah.
crazy.
All right. Comment on the magnitude of your answer.
That's a big jump.
It's a big, big change. Here's the thing that not everybody appreciates. Dilute acids ionize better. than concentrated acids. And why was that?
They're able to solvate better.
Because they have more water to solvate with. Okay. Now, completely new task. You've not seen this before. And if it's in our book, I haven't stumbled across it yet. I haven't had a really strong read of chapter 9. Maybe it's in there. I'm going to give you a table from another book. Here's the question. How badly would your answer have been wrong if you had not done the quadratic solution?
Oh, okay.
Now you can go and calculate. Go ahead and do it. So let's just go ahead and do that with the approximation, because it'll be nice and quick, right? We should all be. I'm teaching the Chemistry 2 students to do this now. It should be something that just kind of happens. Ka 5.62 times 10 to the negative 4 is x squared over 0.0015. So x is the root of 5.62 times 10 to the negative 4 multiplied by 0.0015. And x in our question represents h plus. to,
I got 9.18 times 10 to the -4.
and what was it without?
It was 6.7.
Oh, very good. With the approximation, it's 9.18 times 10 to the -4. With the quadratic, the value is 6.79 times 10 to the -4. How far are they off from each other?
A good bit. A good chunk.
You put one number over the other number and divide them and multiply by 100. Is it really? No.
Wait, 6.79 over 9. Oh, I did the whole thing.
No. Do big over little.
Big over little?
Yeah.
I got 135.22
Okay.
with that percent.
So that's your original number, and then a 35%
Oh, wow.
drift.
That's actually a lot.
Okay. Therefore, 3 dots means therefore 35% difference. If that number comes out to be 100, then your two numbers are the same as each other. There's no difference. This is 35% drifted. Okay, let me show you a completely different way of doing that, where you don't have to do a calculation.
What do you mean?
What do you mean?
Oh, it's a table.
We have a table for it.
Nice. I
You've
like
been
this.
calculating this in the past.
I like this.
We have a table, and this table is the error introduced when you assume that the H plus concentration is small relative to the concentration of the free acid.
Yay. Thank you. So,
Okay, so this is how we set this up. That's called Table 9.4. It's from a book called Skoog,
let's go.
or Skoog. It's a Dutch name. Skoog. I said if this is in our book, I haven't got to the part where it is written down yet. Table 9.4. We have to find the difference between the concentration when you make the assumption and the concentration when you don't. And we do that by taking the concentration of the acid and dividing it by K. It gives us a number. And then we look in the table for that number. And the table tells us how much error to expect. The good news is it's a table, so it's quick. The bad news is it tells you a range. Okay, so our concentration is 0.0015, and K equals 5.62 times 10 to the -4.
Yeah, I got 2.67.
All right, let's go find that in our
So we have a column, and the column is here. This particular book uses the value C for concentration of HA. We've been using square brackets to show us HA. And there's a whole range. We have come up with a value that is 3.
Yeah.
So we find where in this table is 3.
Is there music playing? Am I tripping? No, I'm tripping.
There is no 3.
Yeah.
But there's a 1
Mm-hmm.
and there's a 10.
Yes.
And the table says that when this value is 1, that suggests a deviation of how much percent? It doesn't actually say 1 on the table, it says 10 to the 0. 61%. And when the value is 10, it predicts a deviation of 17. And your answer is 3. So you can interpolate between those two numbers and find out that you should be expecting an answer of about 35%. The answer is somewhere between those two numbers. And your way of doing the extra work has said, yeah, it's 35% error. It's a big error.
Yes.
It's a big, big error. We really, really need to figure that out. So,
The table tells us this safe region right down here at the bottom, that the error associated with introducing the approximation is safe here. You're only introducing a fractional percentage of an error. And that's when the concentration is thousands of, tens of thousands of times larger than the value of K. Okay. We've been going with kind of a rule of thumb of like, hey, if it's 500 times, if the concentration is 500 times bigger than the value of K, go ahead and risk it, because that's going to introduce 3, 4, 5% error.
Yes.
And we can live, general chemistry can live with that. Okay. Which concentration am I using?
0015.
No, I'm going to go back to the original one. I'll show you what's coming next, but it's, you want to do one? It's not quite 12 yet. Going back to the 0.150 moles per liter nitric acid. Find the, we did find the pH, right? Yes, we did. And the, yeah, yes, we did. Just checking. Find the pH of your original nitrous acid . Sodium chloride.
Oh, we have these activities.
concentration of that has not changed.
Yes.
Additional concentration here. So perhaps it was added as a solid,
Mhm.
and that the volume of the granules of the solid was insignificant in changing the volume. And so I have that. Okay. Where are you going to start?
Activities.
How do you get to activity?
Because we have been contaminated, or the solution is
Yeah, but you need something before you can get to activity.
ionic strength.
You need ionic strength. Go do the ionic strength.
What is that concentration times charge?
Let's look at what our ions in solution currently are. I have HNO2, which is in equilibrium with H plus and NO2 minus. These are very small numbers. And I have NaCl. Okay. Remember, these are not in solution, not intact. Only the ions are in solution. So these concentrations are much bigger. Than the concentration of H plus or NO2 minus. So the ions that are in solution that are contributing to the ionic strength are these two, not those. Okay? So first of all, go ahead and find the ionic strength. Mu is 1/2 of the concentration of the Na plus, the charge of the Na plus squared plus the concentration of the chloride multiplied by the charge of the chloride squared. This is one of those one-to-one solves. So you can do the whole calculation, but everything cancels.
Yes.
And just ends up being the concentration that you start with.
Yes.
Okay? So mu gets to be 0.050. Because that's 0.05 multiplied by 1 squared plus 0.05 multiplied by 1 squared all over 2. Okay.
Is there units from you again?
No.
Or-
No.
Great. Wonderful.
Okay. Now you have ionic strength. What you gonna do with it? Okay. What does that involve?
Oh wait, no, we need to find, yeah, we need to find the coefficient.
Yeah, but I forgot.
We find that in the table.
Where was the
The
table?
Yes, the table.
Yes, the tables are coming in.
Coming in hot and heavy.
8-2, I believe. Yep, they 8-1.
Table, yes. Oh, at the.
Wait, are we we're looking for.
So we're looking at
table 8.1, and we're going to be looking at an ionic strength that is 0.050. Is there a column for that?
Yes.
Good. Because sometimes there's not, and you have to interpolate. And which ions are we looking for?
Na plus Cl minus, or
Way
or H
H
plus NO2 minus.
H plus and NO2 minus. Okay.
Right.
These are generating the ionic environment.
Yes.
They are impacting.
Okay.
This.
Got you.
Wait, can you say that one more time?
Yeah, say that one more time.
This is generating the ionic environment.
Yeah.
This change from pure water into a more ionic environment impacts these values.
Yes.
So the values that you have to go find are the activity coefficient for H plus and the activity coefficient for nitrite. It's in the table.
H plus is 0.86.
No, it's a 1 minus charge, so it's going to be in that top group, but they're all jumbled in there together.
Look at you.
Look at you. Yeah,
Look
there it
at
is.
you.
I was like, I can't.
I couldn't see.
I was like, it's online. 0.805.
Okay.
All right, now I have activity coefficients. What am I going to do with them?
Concentration.
Multiply that by our concentration of
The
the
air.
activity.
So the activity of H plus is the concentration of H plus multiplied by its activity coefficient. Yes? Okay. And we're going to use those in the value in the K. So K is the activity of H plus multiplied by the activity of nitrite, all divided by the activity of HNO2, which is equal to the concentrations modified by the activity coefficient.
Ah, I see.
I didn't see that before.
This is the first time we've done it with the denominator.
Yeah.
Now, HNO3 doesn't have an activity coefficient.
It's not a charged species. We set that to be 1.
Okay.
We're just going to use its concentration.
You said that so you made it up, or is it given to us? Like if on a test, for example, if we were to do this, or for a homework.
Oh, I think I would have to say it.
Okay.
Okay.
Yeah.
Nice.
So I would not know.
Where is it?
Now we just plug in X's and stuff.
Mm-hmm.
Oh, okay.
Well, in fact, this would be the long way.
Oh.
Is there a short way?
Yeah.
Of course there's always a short way.
Yeah.
It was obvious. This is a short way.
Ah. So, okay, now.
Everything that's on the board is valid. What if we could just pull the data out that said what the difference is? right? Because Ka is these three numbers divided by each other.
Mm-hmm.
Our new Ka,
Mm-hmm.
the original Ka,
Mm-hmm.
with these factors
Mm-hmm.
attached to it.
Yeah. Oh, well that's nice. I see.
Wait, can you cancel out the concentration since they're all 0.4?
No, because you don't know them,
You don't know.
right?
Our new value for Ka, the one based on activities,
The original K.
is the original Ka now multiplied
The
by,
coefficient of
Yeah.
H-2 divided by the coefficient of H plus and NO2 minus.
mhm,
That's sick. Okay.
cross them over.
Oh my god.
That's
that way.
awesome. Anyways.
You have to write it down before you can see it. H pluses. And NO2 minus. Alright. See, because the rule of the gammas, the activity coefficient, is just to modify
Yes.
what we already have.
Yes.
And the Ka is already taking care of the concentrations. Okay, so Ka, our new Ka, is 5.62 times 10 to the negative 4 multiplied by 1 divided by 0.86 multiplied by 0.0805. This way we don't have to go through the whole
I was
asking, yeah,
Yeah, that would have been a headache.
this is a little bit less work. What's our new number?
I got 8.12 times 10 to the negative 4. But I don't remember. It's in the ballpark. What's that equal to?
Has changed
Yes.
because of its environment. Okay, we've got more to do,
Great.
but we'll put a pin in it. What's left is, let's go ahead and find the H plus and the pH and then the error
Yes.
associated with not using activities.
Mm.
Okay.
Great.
All right.
Sounds good.
I'll see you all next week.
See ya.